Good. Okay, let's go ahead and get started. Just a few administrative announcements. I have problem set 4 for you to pick up. It's a good one. I hope you enjoy. If you haven't picked up your graded problem set 1, I have it here. I also have solutions for problem set 1. Hopefully problem set 2 and maybe even problem set 3. Who knows? The universe could smile on us. We'll be graded for you soon. What's that? An extra week?
Yeah.
Well, but then when would you do the problem set I'm going to give you next week? Well, you have Monday off. This one's not so bad. This one's fun. Oh, you do so much good stuff in this problem set. Oh my God, it's going to be so exciting. I mean, how much time are you spending on the problem set? Let's put it this way. If you want to permanently change the due date of the problem sets to Friday instead of Wednesday, that's fine with me. But I don't want to give you an extra. I want to keep a schedule because I have the problem sets closely in tune with the material, and if we get behind, then you're doing problem sets from stuff weeks ago, and so I'd like to keep on a schedule. If the problem sets are really too difficult and too long, let me know, because then we can discuss that. I mean, how many people find the problem sets long and challenging but educational and fun? Okay, that's the goal. Okay. Okay, but come on, you're deriving the quantization of electric charge. Okay. What's worse? What could possibly be more interesting than that? No?
That was 6.
Okay. Which one was 5?
It was deriving the Harunov bound phase from the Schrödinger equation.
Oh, that's not so hard. It's important. It's important. It's important. Okay. The thing is that every single one of these problems is so precious to me that it would be like tearing out my own eye to remove one from a problem set. So if you feel like the problem sets are really too difficult, come talk to me and I will make them easier, maybe. But I do feel like the problems that you're doing are important and they're interesting. I mean, on this next problem set, what are you doing? You're understanding the origin of structure in the universe. You're understanding quarkonium. You're deriving Gamow formula for radioactive decay, and you're deriving the integer quantum Hall effect. Okay. How could I possibly not ask you to do every single one of those? But don't start it at the last minute. Yes. Okay. What, the physics GRE? Yeah, don't worry about it. It's not very important. Don't worry about it. It's really not very important. No, but I mean, what you're taking at Saturday or Sunday? That'll give you 3 whole days. What better way to relax after taking the physics GRE than deriving the integer quantum Hall effect? Oh, it's the following weekend. Okay. Okay. Listen, I mean, as always, I'm reasonably accommodating about extensions and stuff like that. If there's a systemic effect that affects the whole class, then I'll take that into account. I think the following problem set is actually easier. This one is a little on the longer side. I did remove a problem actually already. But the following one is going to be definitely on the easier side. Okay. I'm a reasonably nice person, okay. Okay, let's go ahead and get started, which means that you guys should stop talking. Thank you. Okay. I also have a bit of a cold, so I'm not going to be able to talk all that loudly. Thank you for your cooperation and silence. Okay. The nice thing about teaching a class when you have 2 kids under the age of 3 is that I can tell you to be quiet, and you'll actually listen to me. What we're going to be discussing today, and roughly for the next week and a half or so, is one of, I think, the most important and most fun subjects that you will see in this class, which is the topic of quantum statistical mechanics. In this portion of the course, we will understand the basic formulation of quantum statistical mechanics in terms of what are known as density matrices or density operators. We'll understand entropy. We'll also spend some time discussing entanglement, what it means, what its implications are for the way that we think about measurement and the collapse of the wave function in quantum mechanics. And also, if we have time, we'll delve a little bit into what this means about quantum information theory and the way that we think about measurements and observations in quantum mechanics. So the basic question that I would like to begin asking is one that if we were actually imagining performing some experiment to test the postulates of quantum mechanics, would of course be very important, which is what if we have imperfect knowledge of the state of a system? So, for example, what if we know that we don't know that we are in an exact state of some system? Here, so far, I'm just thinking classically. And instead, if we imagine that we are considering an ensemble of states, rather than a single state. Classically, this happens all the time. So classically, a state, or I should say an exact state of the system, is described by a point in phase space. But often, if, for example, you prepare some classical system in some state, we don't know the exact state, but we only know some information about the state. For example, if we're considering the state of the air molecules in this room, I, of course, don't know the exact state of all of the molecules in this room, their positions and velocities, but I do know some information. I know expect the temperature of the air molecules in this room. I know other macroscopic variables, such as their volume and their pressure. And so then the question is, classically at least, how would I describe this ensemble of states? If I think not about an exact state, but rather about an ensemble of states, then we would describe such an ensemble by a density on phase space. What do I mean by that? I mean by that some function of the phase space variables, which would be x and p, for a particle moving in one dimension, such that if you wanted to calculate the probability that the system is in a state with a given value of x and p, you would then do that by integrating this probability density in some small neighborhood around that point in phase space. So said a little bit more precisely, rho times dx dp is the probability of finding the state, the system, in, well, we wouldn't want to say exactly at some value of x and p, but in some window in phase space, so say with x between x and x plus dx, and p between p and p plus dp. So that, for example, if you wanted to calculate the probability that the state was in some finite region of phase space, you would integrate this probability density over that region. So, for example, a system at finite temperature, So an ensemble of states at finite temperature is then, by definition, an ensemble of states where the probability density of a given point in phase space is proportional to the exponential of the energy, that is the Hamiltonian, at that point in phase space, divided by the temperature. That's the usual Boltzmann distribution. Whereas, for example, a carefully prepared state with a minus sign. Thank you. That's rho. Yes, and like any sensible person, I use units where Boltzmann's constant is equal to 1. Okay. What is Boltzmann's constant? It's just the definition of temperature. Why not use units where temperature is defined in units of energy instead of Celsius or Fahrenheit or something like that? Who the hell can remember what Boltzmann's constant is anyway? In this class, it's 1. A state which is carefully prepared may have, for example, a density which is very, very close to a delta function. So, for example, if you're a very good experimentalist and you wish to prepare a state which has some exact values of position and momentum, then, well, if you could do it exactly, then the density on phase space would be a product of two delta functions. But if you can only do it very, very well, but not perfectly, then it would be given by the product of two functions of x minus x naught and p minus p naught, for example, that would be very sharply peaked around x equals x naught and p equals p naught. Okay. So, for example, you could imagine that these delta functions are not exact delta functions, but might be very sharply peaked Gaussians or something like that. So that would be an example of a sort of state that we could prepare in classical mechanics. And I think that it's important to emphasize is that when I talk about these densities on phase space, microscopically, the system is in a definite state. I'm not talking, when I talk about a probability of being in a state in this context, I'm not talking about some quantum mechanical amplitude or some very confusing quantum mechanical probability. I'm saying that microscopically our system is in a definite state, and rho describes our ignorance of this state. And what we really should think of is that these probability densities are useful when we prepare many, many, many states and we perform the same experiment many, many times. So, for example, we would imagine repeatedly measuring some variable. So, in classical physics, that would be just some observable A. And then in classical physics, if you have some ensemble of states which are characterized by some probability density, and you were to perform the same measurement, that is to say the same observation of the observable A many, many times, then over many repeated measurements, you would find that the values of A would all average to some expectation value of A, which is the integral of A times rho. And this is upon repeated measurements. And this here, of course, is a statistical average, or a statistical rather than quantum expectation value. And, for example, you could define the variance of the observable A in classical physics just as the difference between the expectation value of A squared and the square of the expectation value of A. Now, that expectation value being a statistical expectation value upon repeated measurements rather than some quantum expectation value. The point, however, is that with enough measurements, rho is an observable. If I hand you a zillion copies of the same system in some ensemble of states characterized by some probability density rho, if I do enough measurements, then I can observe the properties of rho to any desired level of accuracy. So, upon quantization, just like any other observable, it becomes an operator. Which is known as the density operator, or more commonly, the density matrix. So, and in particular, we've seen that rho is just a function of x and p, just like any other observable in classical physics. So it should very naturally become some sort of quantum mechanical operator. So let's try and understand a bit better the properties of this operator. So now I'm going to begin talking about calculating the expectation values of quantum mechanical observables, where we both take a quantum mechanical expectation value and take a statistical average over many measurements. So let's say we have an ensemble of quantum states of some system where the system is in some definite state let's call it alpha I with some probability pi. And of course, the sum over I of the probability is equal to 1. That just means the system's got to be in some state. So the expectation value of some observable, now taking the quantum expectation value, but averaging over repeated measurements of states drawn from this ensemble, is given, of course, by the sum over I, pi, of the quantum expectation value of A in the state alpha I. So, in order to understand this expression a little better, let's try and expand it in some basis. So let's introduce some basis. Let's call it B and B. And let's just insert the identity operator. So these B's will be some complete basis. So I'll just insert the identity operator twice. So you can see that I haven't done anything there, except write this explicitly in terms of not the operator A, but the matrix elements of A in this B basis. But this has the advantage that I can rewrite this simply by reordering the terms. By moving the sum over I inside the sum over B and B prime in order to see that the expectation value of A is really the trace of the operator A times the operator rho, where rho is the sum over I, pi, alpha I, alpha I. So just to state that a little more clearly, you can see that in this third line here, I've written a sum over B and B prime. The sum over B here on the far left and far right just gives me a trace. And the sum over B prime is just the usual way that we write matrix multiplication in quantum mechanics. Okay. You could forget about the sum over B prime if you like, and just get rid of that projection operator onto B prime, and then you would see this would be another way of writing the trace of A times rho. Rho, as advertised, is the density matrix, or density operator, associated to this ensemble of quantum states. So let's stare at that expression for a minute and try and make sense of it. Okay. Remember that, so the first thing that I want to emphasize is that the expression here, where A, the expectation value of A is the trace of A times rho, is supposed to be familiar to you. In particular, it's supposed to be very, very similar to this statement here. So, indeed, the integral dx dp in classical mechanics is the operation that, roughly speaking, becomes a trace over the Hilbert space in quantum physics. And indeed, if you think operationally about what this expression for rho means, what it means is that with some probability pi, we are inserting into the trace the projection operator onto the state alpha I. So this here, I remind you, is the projection operator. Onto alpha I. So I want you to stare at these two equations for a second and think about the case where rho is just, where one of the pi's is equal to 1 and all the others are equal to 0. And then the trace of A times rho is nothing more, nothing less than the expectation value of A in the usual quantum mechanical sense. Okay. It's just the matrix element of A between two states. And all we have done here in writing down this density matrix, when the pi's are not either 1 or 0, is we've written down a more fancy version of this, where you're projecting over lots and lots and lots of different states with different probabilities. Okay. So the density operator is the linear combination of a bunch of projection operators. And this density operator has some properties, which I'll now describe to you. Before I do so, let me pause and see if there are any questions. Okay. People often seem to have a bit of trouble wrapping their heads around the notion of a density operator. I think the way that it's introduced in the textbook may be rather different from how I introduced it here. I don't remember. So you could always take a look at the treatment in the textbook if you want a slightly alternate presentation. Question?
If there's just one sum, though, you're just doing like a projection operator on pi?
Yes. So I here labels the different states that the system might be in. And pi is the probability of being in one of those states. So we sum over all possible states the system could be in of the probability of being that state times the projection operator on that state. Okay. And by definition, okay, the answer that you get when you calculate an expectation value is precisely this guy up here. It's the sum over pi times the expectation value in that state. But I've rewritten it in this language in terms of a trace because, well, it gives me a language, so it means that I can study this density operator rho as an operator, and I can study it just as I would study any other operator in quantum mechanics. I can characterize its properties by taking traces and doing unitary operations and so forth. And so this is a slightly more formal but very useful way of thinking about this ensemble of quantum states. Are there any other questions? Let's investigate this operator in a little bit more detail. So the first thing that you should notice is that the trace of rho is equal to 1. Now, there's two different ways that you can understand that equation. One way is you can understand it by saying that the trace of rho is the expectation value of the operator 1. The expectation value of the operator 1 is 1. Okay. Or you can notice that the trace of rho, if we're assuming that the states are all unit normalized, is just the sum of probabilities. Okay. So the statement that you're definitely in some quantum state is the statement that the trace of rho is equal to 1. The second thing to notice is that because a projection operator is Hermitian, and the probabilities pi are all real, the density operator is a Hermitian operator. Its eigenvalues are real, and it is diagonalizable, just like all the other Hermitian operators that we have encountered in this class. An important point to note, however, is that the density operator is not necessarily a diagonal operator, because these states, alpha I, that I have defined for you, aren't necessarily the basis states that you're going to choose to use to describe your system. So, for example, if we choose a position state basis, for a particle moving in one dimension, then the density operator, which would take the form the integral f of x times the projection operator on to one of these position eigenstates, is a diagonal matrix in the x basis describing an ensemble of states such that the system is in a given position eigenstate with probability f of x. I could have called it rho of x or p of x, but that notation would have gotten maybe a little cumbersome. But, however, this rho is not diagonal in some other basis, say momentum basis. So, just as in classical physics, one can uniquely specify the position and the momentum of a system, meaning that it's possible to define a density matrix that's a function of both x and p that could be very sharply peaked around a given point in phase space. In quantum mechanics, there's some fundamental uncertainty placed by Heisenberg's uncertainty principle, which is reflected by the fact that if you define a density operator, which describes an ensemble of states, each of which is in a position eigenstate with some definite probability, then it's not the case that you're in a definite momentum state with a given probability. Instead, your statistical description of the system is not simply saying that rho is diagonal in momentum space. You just have to specify the goddamn operator. Okay. And the off-diagonal matrix elements of the operator in momentum space would be important. And something that I think I have said before, but is worth saying one more time, let me just say this and then you can ask your question, is that rho really should be thought of as describing classical uncertainty. By which we mean ignorance of the state of the system, not quantum uncertainty. Those are two very different things. And for realistic systems, where we can never specify the initial state of a system with complete precision, both of those uncertainties must be taken into account. And the density matrix formalism is the formalism that we use in order to understand this. Question?
When you say that the system is in a definite state, do you mean that it's in a state that's a linear combination of the basis state with the probability?
No, that's a very important point. Okay. So rho does not mean that you are in a superposition, a quantum mechanical superposition of the alpha i's. Okay. Let's say that I have a two-state system, and I prepare the system in such a way that it's in the state 1 of the system with probability P1 and state 2 of the system with probability P2. Okay. Then I could calculate, repeated expectation values by doing repeated measurements in that ensemble of states, characterized by those probabilities. And the answer that you would get is very different from what you would get if your state were in a quantum superposition of the state, the ket 1 plus the ket 2. Okay. So it's a very important point. In many ways, the uncertainty described by the density operator is much dumber than that which we encounter in quantum mechanics. It's the same uncertainty that you encounter when you study probability for the very first time or when you study classical thermodynamics. In particular, in this density matrix that I have written here, what we are describing is what we're really imagining is a process of repeated measurements of some observable A, where for each measurement, the system is in one of the states alpha I. In the example I gave before, it was either in state 1 or state 2 of the two-state system. Okay? And for each measurement, you're in one of those two states, not in some superposition. And we're just taking an average over many, many such measurements. And the result of that is not going to be the same as a quantum superposition.
There's a probability of being in either one state or
That's right.
another, but it's in one.
That's right. That's why I say we have an ensemble. I mean, this is the important statement, where the system is in a definite state alpha I. This is the issue, in my experience teaching these classes the last 2 years, is that it's that issue that it's really important to wrap your head around. Okay? We're now talking about two different kinds of uncertainty. A real quantum uncertainty of the sort that we are used to studying in this class, and a much dumber uncertainty which just says that I have some ignorance about the state in which I've prepared my system. Okay. Good. Other questions? Okay.
Can you show that? Just like a really simple example?
Can I show some examples?
Just one simple
Okay.
example where the outcome is different. Depending how you interpret it.
Well, I guess I don't. Okay, so let's give an example. Okay, let's take a two-state system. And let's take rho. Let's say that we're in some, the state minus, okay, with some probability P1, and the state plus with some probability P2. Oops, here, let me give myself a little more room. So a two-state system with states plus and minus, okay? And let's take rho to be, say that we're preparing an ensemble of states in this two-state system such that you're in the state minus with some probability P1 and the state plus in some probability P2, where, of course, P2 is 1 minus P1 so that they add up to 1. Okay. And then the expectation value of A is P1 times the expectation value of A in the state minus plus P2 times the expectation value of the state in the state plus. Whereas, for example, you could consider some quantum mechanical superposition. Okay. You could consider a state, I don't know. You could consider the expectation value of A in a state which is given by, say, minus times P1 plus times P2. Okay. So this is a quantum state, which is a quantum superposition of minus and plus. And if you wanted it to look a little more similar, you might put some square roots there. Okay. So that the expectation value of A in that quantum superposition state is P1 times the expectation value of A and minus plus P2 times the expectation value of A and plus a bunch of cross terms. Okay. Plus the square root of P1, P2 times this cross term Okay. So, what is this telling us? This is telling us that this density matrix, which is describing a ensemble of states, which are either plus or minus with some probabilities P1 and P2, is just something that's different from a quantum superposition of the states 1 and 2. So let me give you a little bit more of the examples of quantum mechanical ensembles and how they would be characterized by density operators. Feel free to continue asking questions, of course. So first of all, there is a special kind of density operator, which is referred to as a pure state, and that is an ensemble where one is in a definite quantum state with probability 1. So, pure states are what we have considered in this class so far up until this point. So in a pure state, the density operator is just a projection operator onto that state. And a pure state in addition to having trace of rho equals to 1, as all density operators do, it has rho squared equal to rho, so that the trace of rho squared is equal to 1, in addition to the trace of rho being equal to 1. And, in fact, it's not so hard to see that this uniquely characterizes pure states. To prove that, we could just remember that rho is a Hermitian operator, hence it is diagonalizable. In the basis where rho is diagonal, the trace of rho is the sum of the eigenvalues of rho, and the trace of rho squared is the sum of the squares of the eigenvalues of rho. And you can easily convince yourself that if you have a set of numbers which sum up to 1, and the sum of their squares is also equal to 1, then the only way that that's possible if one of the numbers is equal to 1 and the rest are equal to 0. Okay. So that was a very sketchy proof. If that wasn't clear, prove it. I think it was a problem set in a previous version of this course. Maybe I will or will not assign it as a problem set next week. We'll see how I feel. Depends on how good my weekend is. Okay. Any questions so far? So, states evolve in time, and density operators describe ensembles of states, and so they will evolve in time as well. So, before talking about the evolution of a quantum mechanical ensemble of states, let's talk about a classical ensemble of states. So in classical mechanics, the density operator is a function of x and p, And it evolves according to the following equation of motion. Its time derivative is the Poisson bracket with the Hamiltonian. Did you guys do this in your classical mechanics class? Okay. And in particular, it is this property which is responsible for Liouville's theorem. Okay. So, for example, if you have some phase space and you have a system characterized by a probability density saying that it lives in some region of phase space that I've drawn by a little blob there, then as you evolve in time, this blob will evolve into some other blob. Okay. And Liouville's theorem is the statement that the area of blob 2 is the same as the area of blob 1. Okay. Did you guys see Liouville's theorem in your classical mechanics class? Good. Okay. We can now guess exactly how the density operator will evolve in time. As I've probably beaten to death at this point, the way that we go from classical to quantum mechanics is by replacing Poisson brackets by 1 over IH bar times a classical commutator. And areas in phase space become traces in quantum mechanics. So the statement that areas are preserved in classical mechanics with the statement that the trace of rho will be a constant in quantum mechanics. In particular, it'll be equal to 1. So let's see that. In quantum mechanics, rho is the sum over I, pi, times these projection operators. And it evolves in time. How does it evolve in time? Well, the states alpha I are not necessarily energy eigenstates. So they evolve in time according to Schrödinger's equation. Here, let me write this slightly differently. According to Schrödinger's equation, so one can just take the time derivative of our definition of rho, remembering that these p's are just numbers, to see that the time derivative of rho, what is that? Well, that's the sum over I, pi, times, we first have to take the derivative on the ket alpha I, so we get h times alpha I. Then we have to take the derivative on the bra alpha I, and we get minus alpha I h, using the Hermitian conjugate of the time-dependent Schrödinger equation, which has a minus sign because of the I on the left-hand side of the Schrödinger equation. And I'm using the fact that h is Hermitian, so that h dagger is equal to h. And this, of course, is the commutator of rho with h. With a minus sign up front, actually, if you recall the definition of rho. I should make a comment about this, which is that this looks a lot like the Heisenberg equation of motion for operators, that is to say, observables in the Heisenberg picture, but it has opposite sign. The Heisenberg equation of motion has a plus sign on the right-hand side rather than a minus sign. I'm working in Schrödinger picture after all, so there's no expectation that we should expect the Heisenberg equation of motion to show up. In particular, that minus sign is just something that you have to live with. But one of the consequences of this equation is that if you set the trace of rho at some time t equals 0 equal to 1, then rho will evolve according to this equation of motion. How will rho evolve according to this equation of motion? Well, rho will evolve by conjugation with the unitary time evolution operator, just as in the Heisenberg equation of motion. Just with, because of this minus sign, rho at time t will not be equal to u dagger rho of time 0 u, but u times rho at time 0 u dagger. But the important point is that if you take a trace and use the fact that rho is unitary, then trace at time t must be equal to trace at time 0, which would be equal to 1. This is the quantum version of Liouville's theorem. Questions? Yes?
Sorry, I don't get, where did you get your computation question?
Let me rewrite that a little bit more suggestively. This is h times the sum over I, pi, alpha I, minus the sum over I, pi, alpha I, I don't have quite enough room there, minus the sum over I, pi, alpha I times h. Okay. Do you agree with that rewriting? All I've done is moved the sum over I to the other side of the h. Pi is just a number, it commutes with everything.
You're just applying the Schrödinger equation on like h on p.
Sorry, maybe I'm not understanding exactly what your question is. How did I get this equation here? Yeah. I took the time derivative of I took I h bar d by dt of the definition of rho. And I used the fact that alpha obeys the time-dependent Schrödinger equation. Remember, my definition of a Hilbert space is that I'm allowed to do calculus whenever I want to. Okay. I'm taking the derivative of this operator rho, and the way that I'm taking the derivative of the operator rho is by applying the product rule. So rho is basically a sum of projection operators, bra times ket, and the derivative of rho is if rho is alpha ket times alpha bra, the derivative of rho is the derivative of alpha bra times alpha ket plus alpha bra times the derivative of alpha ket. Sorry, other way around. Bras and kets. Okay. Take that sentence and replace ket with bra and everything will become clear. Sorry, is it clear what I mean here? Okay. I'm using the product rule. The derivative of alpha times alpha is the derivative of alpha times alpha plus alpha times the derivative of alpha. Sorry, I can't make parentheses. There's no word that means the same thing as parentheses, except parentheses. Is everyone clear? Is everyone clear on what I'm doing here? Yeah. Okay. Yeah. I think I made it less clear by answering that question. Just take the derivative of rho and you'll see exactly what I mean. Good question, though. I'm glad you asked. Any other questions? This equation for rho dot as the commutator of rho with h is incredibly interesting because it tells us how to construct ensembles of states that do not evolve in time. So to construct an ensemble that does not evolve in time, we can take rho to be something which commutes with the Hamiltonian. Okay. What's something that commutes with the Hamiltonian? Well, one thing that always commutes with the Hamiltonian is the Hamiltonian. And in particular, any function of the Hamiltonian. So we could take rho to be some function of the Hamiltonian. And then by this equation of motion, which I'll rewrite and put in a box, that ensemble will be time independent. Or if I wish to write this out in the energy eigenstate basis, this is the sum over all energy eigenstates times some function of the energy times the projection operator onto one of the energy eigenstates. So in this case, rho dot will be equal to 0. Simply because all of the energy eigenstates are stationary. They'll evolve with some phase, so the ket will evolve with some phase, and the bra will evolve with an opposite phase, so that rho will be completely time independent. And so we give a name to such states. We call a state, or I should say, an ensemble, which does not evolve in time, an equilibrium configuration, or an equilibrium state. So, for example, the density matrix which describes the Boltzmann distribution is e to the minus Hamiltonian divided by temperature. The operator e to the minus Hamiltonian divided by temperature is the one which is the set of projection operators onto the energy eigenstates, each weighted by the probability e to the minus energy divided by temperature. So that is the quantum mechanical analog of the Boltzmann distribution. I guess there's two n's maybe. Distribution. And the normalization constant n out front is defined so that the trace of rho is equal to 1. So it's conventional to give a name to that normalization constant. We call it 1 over z of t, where z of t is the trace of e to the minus h over t, which is known as the partition function. And just to introduce a bit of notation that I'll be using for the remainder of this course, instead of talking about temperature, it's conventional to use inverse temperature. So we define beta to be 1 over t, so that rho is 1 over z e to the minus beta h, where z is the trace of e to the minus beta h. So another example of a state which does not evolve in time would be a state which is the pure state that's given just by some energy eigenstate. If you put the system in an energy eigenstate, it also won't evolve in time. And so these are the two most natural states to consider when you wish to consider stationary states of a generic quantum system. And we usually give two different names to these ensembles of states. So we call the canonical ensemble the Boltzmann distribution, where rho is 1 over z times e to the minus beta h. And we call the microcanonical ensemble the ensemble describing not fixed temperature, but fixed energy. So the projection operator onto some energy eigenstate. So if we wish to characterize these ensembles roughly, the canonical ensemble is the ensemble where we fix the temperature of the system, but not its energy. The energy will fluctuate. And in the microcanonical ensemble, we fix the energy, but not the temperature. Are there any questions? So you've all seen Boltzmann distributions for sure. I'm just recasting that in a slightly different language in order to use it in quantum mechanical settings. So let me now ask a somewhat more interesting question. Okay. So we've seen that if rho is a function of the Hamiltonian, then that is an equilibrium state of the system. Okay. So we could then ask the question, what is the most general equilibrium configuration? Well, rho needs to commute with the Hamiltonian. And we have a special name for those operators that commute with the Hamiltonian. We call them symmetries. So, operators, let's call them Ni, which commute with the Hamiltonian, are referred to as symmetry operators. And in particular, they lead to constants of motion, namely the eigenvalues of those operators, in the quantum mechanical version of Noether's theorem. And the most general equilibrium state will be one where rho is a function not only of H, but also of these various symmetry operators. Then because all of the n's commute with H, the commutator of rho with H will be equal to 0. And typically, in order to write down such an equation, we'll choose a maximally commuting set of the symmetry operators. Why we do that will become more clear in the following section of this course in about 2 weeks when we discuss the theory of symmetries. But just to reiterate, with an example, let's say that we have a Hamiltonian of, say, a particle in one dimension, or let's do a more interesting example. Let's take a particle in 3 dimension. Then that Hamiltonian commutes not just with itself, but with also the momentum operator P and the generators of angular momentum x cross P. So that means that there are more general sorts of equilibrium configurations that one can consider. So, for example, given a symmetry N, that is to say, an operator that commutes with the Hamiltonian, maybe I shouldn't have called it N, too late, we'll define the operator rho to be some normalization constant, which I'll call 1 over z times e to the minus beta h plus omega times n. So this is the generalization of the canonical ensemble of Boltzmann's distribution to include another symmetry, that is to say, another conserved quantity. And this is usually referred to as the grand canonical ensemble. Where beta is the inverse temperature as usual, and omega is referred to as a thermodynamic potential conjugate to the conserved quantity, that is to say the symmetry n. And so, for different sorts of conserved quantities, that is to say for different sorts of symmetries, we give different names to these potentials. Okay. So for example, if n is the number of particles in some system, then we refer to omega as the chemical potential. If n is the angular momentum of a system about some axis, then we refer to omega as the angular potential. Or if n is the electric charge of a system, then we refer to omega by, let's see who can guess what we call omega. We call it the electric potential. Now, you've encountered other quantities in your life that are also referred to as electric potentials. To understand why the thermodynamic potential, conjugate to electric charge, has the same name as the electric potential, we really need to understand why they're actually the same thing. To see that, let's just stare at this equation here. So, rho is equal to e to the minus beta h plus omega n. So rho was equal to e to the minus beta h plus omega n. It's also e to the minus beta h prime, where h prime is some new Hamiltonian that differs from the old Hamiltonian by 1 over beta times omega n. Does anyone remember what the Hamiltonian of a charged particle in a potential looks like? I wrote it down for you maybe 1 or 2 classes before. I wrote down the Lagrangian. The Hamiltonian is the same. Almost q times phi. The Lagrangian of a particle in a potential is the charge of the particle times the electrostatic potential, phi. Okay. So in the present case, where n is the conserved quantity, that is to say the charge of the particle, then omega is the thing that multiplies the charge of the particle in the potential. That's what we call the electric potential. So that really explains this terminology. So, one of the lessons of this is that the grand canonical ensemble of a system is exactly like the canonical ensemble of a different system with a different Hamiltonian. So the grand canonical ensemble is the same as the canonical ensemble of a different Hamiltonian. So fixing, for example, the potential conjugate to the electric charge. So let's consider an ensemble of systems where I have charged particles. Okay. Then one thing I could do is I could consider an ensemble where the charge is allowed to vary, and I weight the charge. The probability of having a state is e to the minus something times the charge. Then that is identical. The properties of that ensemble are identical to considering a finite temperature ensemble with an electric potential turned on. That's part of the definition of what a potential is. Are there any questions? Presumably you guys have seen grand canonical ensembles. Okay. You've certainly seen chemical potentials before. You may not have seen angular potentials, or you may not have thought of electric potentials in this way. Now, so far I have introduced the canonical and grand canonical ensembles as density operators which happen to be exponentials of the Hamiltonian or of the other conserved quantities of interest, but I haven't explained to you why that is the right thing to consider. And in classical thermodynamics, you've probably seen a derivation of why it's the right thing to consider. Have you, actually? Do you know why the Boltzmann distribution is e to the minus energy over temperature? Well, if you don't know why, you're going to learn it again. Okay. In principle, you have, I'm sure, seen a derivation of it in some sense in your classical thermodynamics class. But now I'd like to derive again for you the why the Boltzmann distribution and the grand canonical ensemble are in some sense the right ensembles to consider from a genuinely quantum mechanical perspective. And in order to understand why these ensembles are the most useful ones to consider, what we really want to think about is why a system is most likely to be in a Boltzmann distribution as opposed to some other distribution. So, in order to do so, we need to introduce some notion of how much ignorance we have about a state. That is to say, we need a precise notion of the disorder of a state, or we could call it the number of active states in an ensemble. That is to say, we need some way of quantifying our ignorance about a quantum state given some density operator. So, for example, if we have a pure state, so that rho is a projection operator, then we have absolute knowledge about the state of the system, and so we would say that the state is ordered. Ordered here is just a fancy way of saying I know exactly what the state is. Whereas, if you took the density operator, which is just the unit operator, okay, the operator that multiplies every state by 1, and I would normalize it by dividing by the dimension of the Hilbert space, then this is the state where in any basis you have equal likelihood of being in any state of the system. Okay. This is maximally disordered. Meaning that I have as little information about the state of the system as I could. Now, what I would like is a way of making sense of this notion of order and disorder that is better than simply using the adjectives ordered and disordered. Okay. That is to say, we seek a functional S of rho, which will be a number associated to every density operator, which I would like to satisfy what I consider to be 3 reasonable properties. The first property is that S will be equal to 0 if and only if rho is in a pure state. The second property is that S of rho should not depend on the basis in which we evaluate it. So, in particular, for all unitary operators U, you could consider the change of basis where alpha goes to U times alpha. And we would not like the entropy, that is to say, this measure of disorder that we are seeking, to depend on this choice of basis. And in fact, this implies that S will be the trace of some function of rho. Okay, so that I suppose is not entirely obvious. Okay. So the fact that S is invariant under conjugation of rho, it means that S is the trace of some function of rho, can be understood if we remember that rho is Hermitian, so that it can be diagonalized, and that S, and that once you diagonalize it, S must be a function of those diagonal elements. That is to say, S must be a function of the eigenvalues of rho. And these eigenvalues can be uniquely determined from trace of rho to the n for n running from 1 up to the dimension of the Hilbert space. How can you see that? Well, what is the trace of rho to the n? It's the sum of the nth powers of all the eigenvalues. And let's say that we have a two-dimensional Hilbert space. Then we could consider trace of rho and trace of rho squared, which would be the sum of the two eigenvalues and the sum of the squares of the eigenvalues. And so if you wanted to solve for those two equations, then if you knew the sum of the eigenvalues and the sum of the squares of the eigenvalues, you would have two equations for two unknowns, and you could solve for those two eigenvalues. Likewise, if you have a three-dimensional Hilbert space, and if you knew the sum of the eigenvalues, the sum of their squares, and the sum of their cubes, that would give you three equations for three unknowns, and you could solve for the eigenvalues in terms of them, and so on and so forth. And in fact, for any, it's just a statement of linear algebra that if you have n by n matrices, then the trace of if A is some n by n matrix, then the trace of A to the n plus 1 can be written as some polynomial in the lower traces of trace of A to the 1 up to trace of A to the nth power. Those are known as trace identities. They're often useful. You may have seen them in the context of 2 by 2 matrices. But hopefully it's clear why this is true. And so if the eigenvalues can be determined by the trace of rho to the n, then that means that, we could just take a general expression for S and write it as a Taylor series, that is to say, as a linear combination of the traces of rho to the n. And in particular, we actually sometimes define an entropy which is known as the Renyi entropy, S sub n, which is the trace of rho to the n. And for a system with a finite dimensional Hilbert space, only S1 up to S of the dimension of the Hilbert space are actually independent due to these trace identities. So, with only these two postulates, that first S of rho equals S of a pure state is equal to 0, and S is invariant under a change of basis, still leaves us with a lot of freedom as to how we can choose this notion of entropy S. Actually, I suppose I should comment, if rho is in a pure state, then trace of rho to the n is equal to 1, not 0, so maybe I would need to subtract 1 or something like that in order to make this definition of the Renyi entropy consistent with my postulate 1, that for a pure state, S is equal to 0. In fact, I believe that in in information theory, when one defines these Renyi entropies, you include some prefactor that's sort of traditional that I don't actually remember off of the top of my head. So the third property that we would like to demand of our entropy is that for two non-interacting systems, let's call them A and B, then the entropy should be additive. S of the density matrix of the combined system should be equal to S of the individual systems, summed over the two systems. Or in other words, S should be extensive. This is our third postulate, that in fact will uniquely determine the form of the entropy. It'll give us what's known as the von Neumann entropy. But in order to make this third postulate precise, I'm going to have to go on a bit of a digression, which will probably occupy us for much of the next class. It's actually a wonderful and entertaining digression into the theory of entanglement, okay, which is basically an answer to the question, how do we describe multiple quantum systems? If you have two classical systems, and you know how to describe the phase space of those two individual systems, then it's very easy to describe the phase space of the combined system. You just take, well, the phase space of the combined system. But in quantum mechanics, the answer is actually somewhat more subtle. And in fact, it's an unusual and I think historically underappreciated fact about quantum mechanics, that once you start considering multiple quantum systems, the number of degrees of freedom of the system, that is to say the dimension of the Hilbert space, grows exponentially with the number of systems that you're considering, rather than linearly in classical mechanics. The dimension of the phase space of n copies of a system is linear in n in classical mechanics, but the dimension of the Hilbert space of n copies of a system in quantum mechanics is exponential in n. And that means that when you consider multiple systems in quantum mechanics, as you would always do when you're considering, for example, thermodynamics or basically anything, any macroscopic system in quantum mechanics, it's going to be vastly more complicated than you might have intuitively thought. And it's this exponential growth of the Hilbert space that is responsible for many of the most interesting effects in quantum mechanics. And so I'm going to really spend a bit of time, paying attention to this. It is this feature which is really responsible for what we think of as the collapse of the wave function. It is this exponential growth in the density in the number of states in a Hilbert space, which allows all of the miracles of quantum computation to be possible. It's why it's possible to solve exponentially difficult problems, computational problems, in a polynomial amount of time in quantum mechanics. It's because the dimension of the Hilbert space, that is to say the number of accessible degrees of freedom you can use to do a computation, grows exponentially in the number of bits you have accessible, rather than polynomially as for a classical computer. So it's also responsible for many of the spooky things that we think about in quantum mechanics, such as quantum teleportation, the EPR paradox, and so forth. So we're going to have a lot of fun. So I'm looking forward to this. Okay, I will see you on Friday with some entangled states.